Lesson 17 is about translations of polynomial functions, and translations fall under a greater group of something called transformations. Transformations are just like any change that we make to a graph, and translations specifically is just like shifting it left, right, or up or down. So you can kind of see like on the table it's labeled on the left side horizontal translation. That would be like side to side, left or right. And then vertical translation, that would be shifting a function up or down. So before we get into the actual problems, we're going to do like a little Desmos exploration. You can get to this link through like the printable version if you want to do it on your own. Just click on it, open in whatever browser you need, and then if you want to sign in with Google, you can. If not, you can just do continue without signing in, and then you can type in your first name if you want. Type in your initials if you want. It doesn't really matter. Okay, so this is the only page of the Desmos activity. Again, it's just an exploration page. So you can see that there's two functions on there. One is a like quadratic where it has squared. One is a cubic where it has x cubed. If you want to just see one at a time, over on the left side there's like the reddish circle with the squiggle, and the purple one, if you click on one, it'll make it disappear. So if I want to just focus on quadratic, I can have that one highlighted. If I want to just focus on cubic, I can have that one highlighted. So I'm going to start with quadratic. So you'll notice that both of the structures of these functions are exactly the same. They both have an x minus h inside the parentheses. And for quadratic, it's squared. For cubic, it is to the third power. And then they have a plus k outside the parentheses. That is the structure for horizontal and vertical translations. So h indicates a horizontal translation, k indicates a vertical translation, and we'll just kind of explore that with the slider. The last thing I want to point out is that inside the parentheses there's an x minus h both times, x minus h. So that's something that we have to consider when we're writing rules, is that that x minus is kind of like embedded in for a horizontal translation. Okay, so if you look at the third line where it says h equals, then there's a little slider underneath it. I'm going to drag that side to side so we can see what it does to the graph. So if I drag it to the right, it gives me a positive h value. Like right now my h value is going up it went from 0 to 4, keeps going up, and as it increases to 5 and so on, it keeps sliding to the right. If I make my h value decrease, I'm bringing it back down towards 0, it's sliding to the left. Now that I'm like negative, I'm even more left of where I started. I started just at like with a vertex of 0, 0. So positive h value takes us to the right. It's a horizontal translation to the right. Think like that's the positive direction for left or right. And then a negative h value would take us to the left, and that's a negative direction for left or right. So one thing to consider is, if I have like an h value of positive 1, I've shifted the graph 1 to the right. If I were to put that h equals 1 into either of the functions above, I might be able to show it. It would end up being x minus 1. If I directly put that like h equals 1 into the function above, because that minus is there. Ignore the line that just popped up. I just wanted us to see like how it's x minus 1 written inside there. If I were to do a negative h value, so let's say I shift it like left 2 from where it originally started, my h value would be negative 2. If I were to take that negative 2 and put it into the function, it would be... Oops, not what I wanted to do. Hold on. I don't think I've ever done this on the notes. Okay, I'm just going to start fresh. It would be x and then minus a negative 2 and then close parentheses, but that minus negative 2 would turn into a plus 2. So minus negative turns into a plus 2. So that's just something to keep in mind when you have like a translation to the left, that double negative turns into a plus, so it's almost like the opposite of what it looks like. Sometimes like a translation to the right looks like it should be left because the negative is still there. Sometimes a translation to the left looks like it should go to the right because it's a positive or a plus that plus a number. Okay, that's something you just kind of takes practice to get more comfortable with, but I just wanted to point it out right now. Okay, so I'm going to bring h back to 0, so we're kind of back where we started with a vertex at 0, 0, and then we'll look at k. So you'll see there's like a plus k at the end of both the functions in line 1 and line 2. If I make the k value positive, it shifts my graph up. It's a vertical translation. If I make my k value negative, it shifts my graph down. It's a like vertical translation in the negative direction. Because at the end of each function is just plus k, I don't have to worry about like flipping the sign or anything like that. It's generally like what it looks like it should be with a vertical translation. So positive k shifting up, negative k shifting down, just like with h where positive h was to the right, negative h was to the left. It's just a little bit less confusing once we go to write the rules or identify transformations from the rules because it's a plus k in the rule itself as opposed to a minus h. Okay, so if we look at the cubic function, same rules apply, it's just a different function. We call it a parent function, the one that we're starting with. For a quadratic, a parent function would just be like f of x equals x squared. For a cubic function, it would be x cubed. So still horizontal translation, if h is positive, that shifts it to the right. If h is negative, that shifts it to the left. And then for vertical, if k is positive, that shifts it up. If k is negative, it shifts it down. And then lastly, I just want to compare the two graphs together. So obviously like different kind of starting places, different parent functions, but no matter what, the translations are the same. So like if I make h a like positive 1, the graphs are moving together. They're both moving 1 unit to the right, or like 2 units to the right, or if it's negative, they're both moving x amount of units to the left, and so on. And then same thing for vertical, you'll see the graphs moving together. So translations don't like really vary from function to function. They always work the same way, just kind of where we're starting changes. So you'll see if k is positive, it shifts the graph up like 3 units here. Negative shifts it down 2 units here because k is negative 2, and so on. Okay, and this link will always be like active as long as you're in this class, so you can always kind of come back here and play around with it if you'd like. You can also just use this same page if you wanted to type in another function and see how it changes as well. So now we're going to go ahead and like write transformations within this. So number 1, we're going to start with horizontal translations. So the like function notation for horizontal translations is f of x minus h, which means that we're changing the like input of the function, which kind of goes back to, the input is the x value, and the x value, the point, controls like where it is left or right on the graph. So it all is related. So we can say like this like x minus h thing, it indicates a change to the input. Try to combine those words, to the input, and then another word that you'll see in this case, like instead of input, you'll see it in the workbooks is the word argument. It just means that like part that's inside the parentheses. Okay, so number 1, f of x is equal to x squared plus 6 is translated 2 units to the right. To get g of x, write a rule for g of x. So when you say when you see the phrase or instructions like write a rule, you're writing a new function. You're writing a function that incorporates that translation. So 2 units to the right, that would mean that h equals positive 2. So h is always like the value of our horizontal translation. If we're going to the right, it would be positive. If we're going to the left, it would be negative. So I'm going to rewrite the function down here. The original function is f of x equals x squared plus 6. And then this like f of x minus h, I have to take my h and put it in here, and I just rewrite f of x that way. So instead of like regular f of x, I would write it as f of x minus 2 in this case because h is 2. Remember that the minus is already there. And then what that actually means for like writing the new function is wherever there's an x in the function, so like there was originally an x where the x squared was, it gets replaced with x minus 2. So like x is changing to x minus 2, so will all the x's in the function. Even if there's more than one, they all get changed. So in this case, like the x by the x squared doesn't have parentheses, but we need to put the parentheses there to make sure that we're including the minus 2 with it. So instead of x squared, it'll be in parentheses squared x minus 2. And then the rest of the function stays the same, so we would still have that plus 6 there at the end. So one more time, I'm just going to go through that. So f of x minus 2 means that we're shifting to the right 2 units. If we're changing to f of x minus 2, that means that everywhere there was an x originally in the function, so there was one right here, it gets replaced with x minus 2. And then if you need to throw in parentheses, add parentheses. You most likely will for like a horizontal translation. I can't think of a situation where you wouldn't unless they were already there. And then the rest of the equation or function stays the same. So like that plus 6, we just tack that on at the end. And then the last little part of the problem is it just said in the directions to write a rule for g of x, and it was saying that, f of x is translated to get g of x. So our final answer would just be we would want to name the new function g of x. So it would just be g of x is equal to, and then it's just all of this. We're just naming that new function g of x. So is equal to x minus 2 squared plus 6. So g of x is equal to x minus 2 squared plus 6, and we'll just leave it like that. Okay, so number 2. So f of x equals 2x minus 3 is translated 5 units to the left to get f prime of x. Write a rule for f prime of x. It means the same thing as like changing the name completely, just another way of writing like a transform function. So 5 units to the left. If we're going 5 to the left, that would mean that h is negative 5, since left is the negative direction. So I'm going to treat this the same way. I'm going to start with the original function f of x equals 2x minus 3. And then I'm going to rewrite it in like the function notation with the translation in there. So function notation, like the little formula for horizontal translation, is f of x minus h. So instead of minus h, I have to put my like negative 5 in there. But if I have a double negative, that turns into a positive. So we wouldn't write like f of x minus negative 5. We would just simplify it to f of x plus 5. And then what that means for our actual function is, wherever, so x inside the parentheses or inside the argument change to x plus 5. So does every single x in the function. Again, if there's more than one, you would change all of them. So this would become 2. And then instead of just x, it would be parentheses x plus 5. And then I would just bring down the minus 3 at the end. So minus 3. And then notice like the structure of the equation is basically staying the same. So it's 2 and then times x, but now x is x plus 5. And then the minus 3 is the same at the end. So for number 1, we didn't do any simplifying because the equation that or the function that we got for our final answer, that was in like a specific form. It was in vertex form for a quadratic, which is like a very useful form. So we just want to leave it like that. We didn't necessarily want to like change it to standard form or anything like that by foiling it. Number 2 is linear, meaning like it's just x to the first power is the highest power. This is not really a form that's useful for linear, so we do just kind of want to simplify this. So we would just go ahead and distribute the 2. So 2 times x is 2x. 2 times 5 is plus 10. And then bring down the minus 3, and then we can combine like terms, the 10 and the negative 3. So it'd be equal to 2x, and then 10 minus 3, so plus 7. And then the instructions for this one said to write a rule for f prime, or that f of x was translated to get f prime of x. So that's just what we'll title our final answer. It'll be f prime of x is equal to 2x plus 7. And then the last one for horizontal translations, for number 3, it says f of x is equal to x squared. So that's taking like our parent function for a quadratic, like the most basic form of a quadratic. Write a rule for f of x based on the translation in the graph. So in this case, like it doesn't tell us what the translation is. We have to look at the graph and find it. So I think the easiest way to do that for a quadratic is to look at where the vertex is and how it changes, and then just make sure that in general the shape of the graph stays exactly the same. Right now we don't have to worry about that, but if the shape of the graph changes, there could be like different transformations happening as well. So if we look at the vertex, there's on f of x, it was right here at 0, 0, and on f prime of x, it was right there at 2. So we're shifting 2 to the right. So if we're shifting 2 to the right, that would mean that h equals positive 2. So rewrite the original function, it's f of x equals x squared. And then I still have to use that little kind of like function formula for horizontal translation. It's f of x minus h. So I'm going to rewrite my f of x that way, but with my actual h value of 2 in there. So it'd be f of x minus 2. And so the input x was changed to x minus 2, so will every x in the function. Right now it's just that 1. And I do need to put in parentheses since they're not already there in this case, and I'm like putting in a quantity for the input, x minus 2. So x minus 2 in parentheses squared. So the x changes to x minus 2. I know there's only one other little part of the function, but everything else would stay the same. Just the squared part in this case stays exactly the same. And then same thing here, we want to write a rule for f prime of x. That's the new one over here. Over here is f prime of x, so we'll just write our final answer like that. So f prime of x is equal to this entire piece. We don't need to change that. Like I said, you could like FOIL it and put it in standard form, but that's technically in vertex form as well right now, so there's no need to change it really. So parentheses x minus 2 squared. So f prime of x equals x minus 2 squared. Okay, and then for number 4, going back up to the top, so we're on to vertical translations, which the like kind of function formula for vertical translations is this f of x plus k. Typically, like vertical translations are a little bit easier to apply. I might add one more example at the end to kind of show you. But with horizontal translations, like we're changing the input, so we'd have to change every other or every single x within the function. Our function just had like 1x, so that's where I may go back and change something. With vertical translations, you're just adding k, a constant number, to the end of it. So you're not having to change like multiple parts potentially of the function. You're just always having to tack on a constant number at the end. So for number 4, f of x equals x to the third power minus 3 is translated 10 units up to get f prime of x. Write a rule for f prime of x. So we're translated 10 units up. If we're going up or down, that's k. And since we're going up, k would be positive 10. So we'll start it the same way, write our original function, f of x equals x to the third power minus 3, and then rewriting the rule with our k involved. So it would be like if there's a vertical translation, f of x plus k, but we know k is 10, so we're going to do f of x plus 10. And what that means is, okay, so f of x, like that part stays exactly the same. That's this. So we're just going to copy that down. So x cubed, minus 3. The only thing that changes is we're adding a constant to the end. We're essentially changing like the original output value, which output value, like that is the y coordinate of the point. So that goes back to like how tall the graph is. So we're changing like the height of the graph and it connects it back to vertical. So it's all related. So we've copied down our f of x, and then the only change is this plus 10 is getting added to the end. I'm just going to add it to the end right there. And then if you can simplify, you want to. So like we have like terms right here, we can add those. And then we're supposed to name our final function f prime of x. So f of x is translated to get f prime of x, so that's how we'll title our final answer. So f prime of x is equal to x to the third power, and then if we combine like terms, negative 3 plus 10 is 7. So f prime of x equals x cubed plus 7. Okay, and then for number 5, I think I'm actually going to skip number 5 for now. I'm going to go back and make that kind of like a combo problem where we do a vertical and a horizontal translation. So for number 6, it's f of x equals x minus 1 to the fourth plus 1, red rule for f prime of x based on the translation in the graph. You can see I had to fix a little minus to a plus sign right there. It'll be fixed by the time you guys are able to print it if you normally print them, but just keep that in mind. Okay, so same thing as like number 3, where we have to look at what translation is happening like in the graph. This is a quartic function this time, but it kind of works the same way, where we can have like a vertex point to pick from and see where the graph is changing. Really, like, you don't have to pick a like vertex. You can pick any like kind of point that stands out to you and see how it changes to get to the next one. So f of x, that's the like green graph, so we'll start there. The vertex for that one, the scaling on this graph is a little bit inconsistent, so like you can see that the x-axis is scaled by 1s, and then like for every grid line, and then the y-axis is like the 1 is halfway up, and then the 2 is on the first grid line, so it's a little bit different. So this vertex for f of x is 1, 1, even though it kind of looks not like 1, 1. And then for f prime of x, we're going right 1 and then down 1, so it's 1, negative 1. And then just kind of like looking at those points helps us to find the translation. Sometimes you don't necessarily have to draw them, but if you get a little bit stuck, I would recommend it. So between those 2 points, from f of x to f prime of x, the like green to the reddish, we're going down 2, because we're going from like a y value of 1 down to negative 1. The x value doesn't change. So if we're going down 2, that would mean that k is negative 2. And then we'll start the same way. We'll write our original function. So f of x equals x minus 1 to the fourth, and then plus 1. The nice thing about a vertical translation especially is how like difficult, or like, I guess, I don't want to even say difficult, but like how complex the like original function is, like how many different things are going on with it, doesn't like really impact that much, or at least as much as like a horizontal translation. With a vertical translation, no matter what, you just get to like tack the constant number onto the end. So our like little formula for vertical notation is f of x plus k. But we know that k equals negative 2. So I'm going to take off that plus k and I'm going to put a minus 2 there. And then you'll notice, so f of x is staying exactly the same. So this whole thing is going to stay exactly the same, meaning there's like no changes to the input or the argument. There's no change we need to make to x inside the parentheses or anything like that. We just copy it down exactly. So x minus 1 to the fourth power plus 1. And then the only change is happening like after f of x is that minus 2. So this is f of x exactly. And then after that, we can just tack on the minus 2. And then our new function, we're supposed to title f prime of x. So we'll say f prime of x is equal to, and I just need to combine like terms is the only simplifying I need to do here. So that 1 minus 2, I need to combine those just to get it simplified. So it'll be x minus 1 to the fourth power in parentheses, and then 1 minus 2 is negative 1. And then same thing as one of our like horizontal translations. We don't need to like multiply x minus 1 to the fourth like all the way out. This is like vertex form for a quartic function technically, so it's fine as is. Like that's a perfectly good form to leave it in. So f prime of x is equal to x minus 1 to the 4th power minus 1. Okay, and then we're going to go back to number 5. I'm going to make some changes to number 5, though, just to get an example in with like both vertical and horizontal translations at once. So number 5 originally says f of x equals x to the 4th plus 4x cubed plus 8 is translated 6 units down to get g of x, radical for g of x. I'm also going to say like 4 units to the left. Okay, so 6 units down, that would be a k value of negative 6 because k is up or down. And then 4 units to the left or right, that's my like h value. So since h is, h is a horizontal translation, and then since we're going to the left, h would be negative 4. So we'll start with the original function. So it'll be f of x equals x to the 4th plus 4x to the 3rd power plus 8. And then a formula that we can use that incorporates both a horizontal and a vertical translation would be f of x minus h, and then close parentheses, and then the plus k at the end. So if we go back and we look at like the 2 original ones, these ones that are highlighted up here at the top, it's just kind of a combination of those two. So the f of x changes to f of x minus h, and then the plus k gets tacked on at the end. This is how we would write both vertical and horizontal translations. So now I'm just going to take each of like the h and k values and substitute them in. So h was negative 4. So instead of minus h, it'd be minus negative 4. But we wouldn't, I wrote h again, minus negative 4. It's basically like an upside down h of minus negative 4. And now we just want to simplify it. So we would never leave it as like a double negative, but x minus negative 4 would simplify to x plus 4. And then for k is negative 6. So instead of plus k, it would be like plus negative 6. But again, we wouldn't like just like leave a plus negative. We would just change it to a minus. So instead of plus negative 6, we'll write it as minus 6. Okay, so now we have our like function form of it structured to get those transformations in. What that means in terms of like the changes I make now is the input or the argument, what was inside parentheses, changes from x to x plus 4. So now that means anywhere where there's an x inside the function changes to x plus 4. And then this like minus 6 got tacked on at the end. We just have to tack it on at the end of ours. So we'll worry about the like x's changing first, the input for the horizontal translation. So instead of x to the 4th, it would be x plus 4 to the 4th power. So that first one changes. And then for the second term, it's a 4x cubed. So that would become plus 4. And then instead of x, it would become x plus 4 to the 3rd power. And then the third term is plus 8. There's no x there, so I don't need to change it. I just write it as plus 8. Okay, so what we've done so far is we have done like the horizontal translation. We changed f of x into just this. Now we just need to incorporate the vertical translation, so I just need to subtract 6 off the end of it. I just need to tack that constant on to the end of it, so minus 6 at the end. And then we would just check for like terms. Okay, so before we check for like terms, I just want to like kind of compare how the structure of the like function has not really changed all that much. So like x to the 4th changed to x plus 4 to the 4th because we changed our like x's into x plus 4's. This was a 4x to the 3rd power. It became a 4 times x plus 4 to the 3rd power. The 8 didn't have an x with it, so it just got copied down. And then lastly, to do the vertical translation, we just had to subtract 6 at the end. And then now we can go ahead and combine like terms. We can combine the 8 and the -6. So we're supposed to name our like final function g of x. So we'll do g of x equals, and then everything else copies down. We just combine like terms at the end. We don't need to like multiply all those out or anything like that. So x plus 4 to the 4th power plus 4 times x plus 4 to the 3rd power, and then plus 8 minus 6, so plus 2. So g of x is equal to x plus 4 to the 4th plus 4 times x plus 4 to the 3rd, and then plus 2 at the end. Okay, so we'll do more like types of transformations in a later lesson, but this is just, like I said, horizontal different types of transformations. I might have said translations. I don't know. Different types of transformations, like in general. These are just translations, so just shifting left, right, up, or down. But big thing to know is that we use these formulas to kind of see how to change the structure of our function. And then I'm going to write the kind of double one at the top so you can add it in as well. So to incorporate both, it would be f of x minus h and then plus k at the end.